Okay, so since it's been a while, I think it's probably worth going back and backtracking a few slides and starting over with MO theory. So notice I put a few of these slides completed up online. I went through them a little fast last time, so they're up there if you need them. So remember that this is what we're treating, this is the quantum mechanical treatment of this, okay? This is taking all of that stuff that we learned about wave functions and making orbitals and using that to figure out how bonding works. It's a linear combination of atomic orbitals, which we said means that we're either adding or subtracting the wave functions, okay? So we're taking those wave functions and then we're adding or subtracting them together and we're getting these new orbitals out of it. So this is the way that yields a little bit better agreement, meaning that if you try and compare hybridization and MO theory to the actual experiments, in general, MO theory does a slightly better job of predicting it. Hybridization does a good job, but MO theory does a little bit better. But it's a lot more complicated, and so we don't use it quite as much when we have real big, long, complicated molecules. And if you do, you are doing very complex math with computers. Okay, so this is where we're kind of going to veer off significantly from hybridization theory. Before, we just had these orbitals, and if we had electrons in those orbitals and they were overlapping, we had bonds. Now, MO theory is a little bit different. We have bonding orbitals and we have anti-bonding orbitals. So what happens is that, well, and same thing that happens in hybridization, where if you start with 2 orbitals, how many do you get? 2. If you start with 6 orbitals, how many do you get? 6. Okay? So those are the 2 big numbers we're going to be dealing with, 2 and 6 this time. So same sort of rules apply. Now, when you do this, let's say we're just combining 2 orbitals together. You're going to end up with a bonding orbital, and you're going to end up with an anti-bonding orbital. If you put electrons in the bonding orbital, it makes the bond stronger. Take a guess what happens if you put it in the anti-bonding orbital. Gets weaker. Good. So electrons in bonding orbitals make it stronger. Electrons in anti-bonding orbitals make the bond weaker. Or a different way of saying that is it adds to the bond order, or it subtracts from the bond order. So the way you want to think about bond order is like how we thought about double bonds and single bonds before. A single bond, in this case, we'll think of as a bond order of 1. A double bond, a bond order of 2. But what we'll see is we can get bond orders of a half and things in this as well. Okay. So we have to backtrack a little bit and refresh your memory about waves, because this is what we're back to dealing with, right? We're dealing with these wave functions and therefore waves. So remember how they interfere with each other. You can have 2 different types of interference. If you have constructive interference, are they adding or subtracting? Adding. Destructive? Subtracting. Okay? So just quick reminder on this. If you have 2 waves that look like this and they're interfering constructively, it's going to make them bigger, right? Now, if you have them exactly opposite from each other, then it's going to completely cancel. Now, of course, they don't have to exactly be over top of each other in exactly this manner, but you get the idea. And if you can remember back to when you took like an Algebra 2 class of some sort, and you actually had to go through and sort of add these points together, you'd have actually the number here and the number here, and you'd add them together to see what you got. And the same thing here, you'd add this point here and this point here to see what you got. It's the same sort of idea. It's just, very, just kind of looking at it. Okay, so now let's look at this in terms of orbitals instead. I'll give you a sec. Looks like people are still writing. Okay. So now when we apply this to orbitals, so let's say we have 2 hydrogen atoms, okay? So we're starting simple. So what sort of orbitals do I have drawn here then? Just s orbitals. Now we can combine these. So this would be 1 hydrogen atom, this would be your other hydrogen atom. And we're going to take the s orbitals and we're going to combine them together. How many orbitals are we starting with? So how many do you think we're going to get? 2. And one of those is going to be a bonding orbital and one is going to be an anti-bonding orbital. Which one do you think is higher in energy, bonding or anti-bonding? Well, I guess I'll tell you. The anti-bonding. So the higher energy one is going to be anti-bonding, okay? So you add to the bonding orbital first, and then you add to the anti-bonding. So I have this sort of drawn out, but this is basically an energy level diagram, right? Same idea as when we did the atomic energy level diagrams for each individual atoms. Well, now we have an MO diagram with the energy levels. So we'll still have this E, we'll still have this. So if you add the two together, you end up with a bonding orbital. And if you subtract the two together, you end up with an anti-bonding orbital. Now let's look at how we would normally draw this, because drawing this would get really tedious, especially when we start getting into, p orbitals and things of that sort. Well, I'll give you this real fast. Okay, so this just goes over what I said. So we have the anti-bonding molecular orbital here. We call this sigma star, okay? Now we have the bonding orbital here, and we call this sigma, no star. So what do we think the star represents? Anti-bonding. Whenever you have an anti-bonding orbital, you put a little star next to it, and that signifies that it's anti-bonding. This sigma represents the shape. Just like when we talked about sigma and pi bonds and hybridization and valence bond theory, and that represented the shape. We always talked about the sigma bonds being overlapping end on end. The same rule applies here. This is going to refer to the shape of the bond, or the bond orbital. Okay, so drawn out in sort of the standard way of how we look at these, how we've been drawing them up until now. If we notice, this is going sort of through the first couple elements of the periodic table, or first four. So here we would have hydrogen. Now, hydrogen each has how many electrons? 1, right? So I have this drawn here. When you draw these MO diagrams, you need to draw the atomic diagrams too, okay? If I tell you on an exam to draw me an MO diagram and you just draw this middle part right here, that's not going to be correct. You're going to lose some points. So make sure you draw these in. So I already did that, so that's just sort of what we're used to drawing. Notice we draw 2 of them, right? Because we have a hydrogen over here and a hydrogen over here. Now, how many electrons do we have total in hydrogen? 2. So that means that we're going to have too many, or how many electrons when we fill into the MO diagram? 2. Where do you think we should put them? Low energy, high energy, 1 in each? Low energy, okay? So same rules apply as when we were doing atomic orbital diagrams, where we start at the low energy and work our way up. Same rules apply here. So we put them both there. We also still do spin up, spin down, just like before. Each orbital can still only hold 2 electrons like before. So all those same sorts of rules apply. Now, one of the big questions that get asked when people start doing a lot of these is, well, if you tell me to draw it, do I have to put these labels in? Yes, you have to put the labels in. So you have to have the sigma, and you also have to have the little subscript that tells us where it came from. So these came from the 1s orbitals. Okay, we took 1s orbitals, mixed them together, and we got these new orbitals. So that's what the subscript means. It's where it comes from. Do you have to have the star to get the point? Yes, right? That tells you that it's anti-bonding. That tells you that something in this orbital is taking away from the bond. So you have to draw all of this to get the points. Now, helium is the same sort of idea, but how many electrons are we dealing with now? 4. So we fill them in, same rules as before. We do 1, 2, and then we move up to the higher energy if we have to. So we fill that in. Okay? So that sort of gets us through that first, top little row of the periodic table. Now, when we move into lithium and beryllium, now we have 2s orbitals to work with too. So notice they get a little bit more complicated. But it's really just this redrawn up here, and this redrawn up here. What's the big thing that changes from here to here? The numbers, right? Now we have 2, because we're in the second energy level. Okay, so when we look at this, how many electrons do we have total in this lithium? 6. So we fill in. We start at the bottom and we go up. We don't have to worry about where these electrons really come from. When we start getting into some more complicated ones, we'll care a little bit, but not even then. Once we know how many electrons we have, and we have them filled into our atomic level, or our atomic energy level diagram, now it's just a matter of filling in. We have 6 electrons, we start at the bottom and work our way up. And we're done. Okay? Same thing for beryllium now. We have 8, so we go through and we fill in, and we're done. It doesn't matter where they came from. I wasn't sitting here concentrating on the fact that, okay, well, I have 4 here, so I put all 4 in here, and 2 here, and I put 2 in there. I could have, I would have got the same answer, but you don't have to really worry about that. It's just filling in. And again, notice I put over here, I put the atomic level I put the atomic energy level diagrams. So you have to draw those in. You have to label them. You have to draw these in. You have to label those with subscripts and stars where necessary. Okay? All right. Now let's take a moment and talk about bond order. We'll see a bunch more of these. We'll see the more complicated ones in a minute. But I want to talk about bond order first and how we figure that out. Okay, so we've already talked about sort of whether something adds or subtracts to a bond order, but not exactly how to calculate it. So if you put electrons in a bonding order, or in a bonding orbital, we've said that they add. What happens if you put one to an antibonding orbital? Subtracts, good. Okay. Now, each one is going to add or subtract half a bond. Does this make sense with what we already know? How many, with what we've talked about up until this moment in time, how many electrons make a bond? 2, right? In a single bond, we would have how many electrons? 2. In a double bond, how many would we have? 4. Triple bond? 6. Okay? So that already kind of flows with the logic that we have. We know that in a single bond, we have 2 electrons, which means that each electron would add, half. That's what happens here. Or subtract if it's in an antibonding orbital. So this is sort of the formula for it, but quite honestly, I think it's almost easier to just think about rather than using the formula. Either way you want is fine. We'll walk through it both. So this formula says that you take the number of bonding electrons. So the electrons that are where? Bonding orbital or antibonding orbital? Bonding orbital. You subtract the number that are in the antibonding orbital, and then you divide by 2. And that just counts for the fact that each electron only really counts for half, right? We're not actually, if you add an electron to a bonding orbital, it's only adding in half, not a full one. So you can roughly think of this corresponding to single, double, or triple bonds. It's sort of the equivalent thought process, just in a different theory. And you're allowed to have bond orders of decimal points, which is nice. Because before we couldn't really do that, right? I mean, we could talk about it, but how did we have to draw in those bond orders? Think through your sapling homework. Think about I think it was an 03 maybe that you had to draw. How did you have to draw that in order to see what the bonds look like? Resonance structures, right? So we couldn't, there wasn't really a distinctive way of drawing in, half a bond order. We just kind of had to say it. Now we have that. Okay, so let's go back and look at these again and actually calculate out the bond orders for each one. So first, let's look at hydrogen. So how many electrons do we have in bonding orbitals? Just this one, right? Are these bonding orbitals? No, those aren't even really there anymore, right? We've taken those and we've made our molecular orbitals out of them. These are just our atomic orbitals. So we're just looking at these 2. This is our bonding. This is our antibonding. So how many electrons do we have in the bonding orbital? 2. How many in the antibonding? So what is our bond order? 1, right? 2 minus 0 equals, divided by 2 is 1. Okay. So do we think hydrogen is going to be a molecule? Is H2 going to be something that exists? Yeah. And when we draw it, what did we always draw hydrogen with? What kind of bond? Single bond, which goes along with this quite well. Okay, now look at helium. How many electrons do we have in the bonding orbitals? Okay, how many in the antibonding? 2. Okay, so according to our formula then, that's 2 minus 2 is 0, divided by 2 is still 0. So 0. The other way I kind of, if you don't want to fill into the formula all the time, well, you have 2 here and 2 here, they completely cancel out, so that's going to be 0. Slightly faster way of thinking about it. So you end up with this. So do we think that that helium, diatomic helium, is going to be something that exists in nature? No, right? Bond order of 0, that's not stable. That's not going to be something that happens. Okay, now let's look at lithium. So how many electrons do we have in bonding orbitals? 4. 1, 2, 3, 4. And how many do we have in antibonding orbitals? 2. So what is our bond order? Okay, let's start over. How many do we have in bonding orbitals? How many do we have in antibonding orbitals? And what's that divided by 2? All right. Okay. Now what about beryllium? 0. Okay, so two different ways we can think about it. We can fill into the formula and say, well, we have how many in bonding orbitals? 4, 2 here and 2 here. How many in anti-bonding orbitals? 2 here and 2 here, right? Anything, maybe we should go back and talk about bonding and anti-bonding orbitals one more time. If something doesn't have a star on it, that's a bonding orbital. If something does have a star on it, that's your anti-bonding orbital, right? So any of these, here and here, those are your bonding orbitals. Are we counting these on the side at all? No, those are our atomic level diagrams. We put them there to kind of show where the orbitals are coming from, but those are not counting, we're not counting those electrons as part of our bonds here. We're just looking at the MO diagram, which is in the center. Okay? So we have how many electrons in bonding orbitals? 4. How many in anti-bonding orbitals? 4. So 4 minus 4 is, okay, so we have a bond order of 0. That should be 0. Quick fix there. Okay. There we go. All right. So now let's go to sort of next complication level. What do you think we're going to start doing with now? P orbitals. So now we have to combine in P orbitals. Now there's a couple of different ways we can do this because we have multiple P orbitals, right? So this is a diagram from your book. Okay, so we're taking these two P orbitals and these two P orbitals and we're combining them together. Now how many P orbitals total do we have in an atom? 3, and we're combining 2 atoms together, so how many do we have? 6. So how many orbitals are we going to get out of this whole thing? 6. Okay, so once we combine all of these together, we're going to end up with 6. Now here I only have 4 kind of shown. So why do you think that is? Think back to what our other things look like. When we were doing hybridization, we could overlap them 2 different ways, right? What was the first way that makes a sigma bond? End on end, right? We sort of took the long direction and kind of went like that and overlapped them. And then what was the other way that we could do it? Side on side, right? So if we imagine a lobe here and a lobe here and a lobe here and a lobe here, we need to get some balloons. We overlap them side on side. But we could do that in 2 different dimensions, right? If we did this in this dimension, this in this dimension, we could go that way too, right? So this is all, this same sort of thing applies here. It's just now we're treating it quantum mechanically rather than sort of the other way. So here what we're doing, if we look at this, this looks like your p orbital you're used to, right? You're thinking of it as sort of your 2 lobes of a balloon. And you can overlap them 2 different ways because of the positive and negative lobes. So you can get a bonding orbital or you can get an anti-bonding orbital. And that's what they look like. Okay? So this is sort of your pictures of what a bonding orbital and an anti-bonding orbital looks like. Now that's the end-on-end direction. So you can kind of see them, this one and this one coming together. Now what if we do it side on side? Now you get this sort of pattern. What does that look really similar to that we've already talked about? Your pi bond, right? So same sort of idea, it's just a slightly more mathematical treatment of it. And then you have your anti-bonding orbital too. Now, of course, this one you could do in the other dimension as well. And that's where the other one would come from. So you would have 1 of these and you would have 2 of these. Okay? But they would look the same, just 1 in one dimension, 1 in the other. Okay. So when we go through and we make these, so I've already shown you a few of the simpler ones, but this is sort of my way of, stepping out all of the steps for you before we move on to the more complicated ones. First step is you're going to draw your atomic diagrams, okay? So the same things that we drew on the last midterm material, you're going to need to be able to do that again. So you're going to draw your atomic orbital diagrams off to the sides, all right? You're going to fill in the electrons that you normally would. So, something like carbon, you would put your electrons in your s orbital and your electrons in your p orbitals just like before. Now, this is the part that's going to be a little weird until we actually look at it. I say decide on which order the energy diagram would follow. We're going to just leave that one alone for a moment. And then I'll show you when I have pictures of them. Okay, so then you're going to add up all the valence electrons. In your book, sometimes they'll draw in the 1s and all the way up above. All I really care for the MO diagrams is that you draw the valence shell, right? So if we're talking about hydrogen and helium, just draw the 1s. If we're talking about all of the second rows, just draw the 2s and 2p's. So once we draw those in, you're going to take the valence electrons from your atomic diagrams. You're going to add up all of those electrons, which is what we did for lithium and beryllium, right? We said, okay, well, there's this many electrons. We added them all up, and we filled them in. Same thing here. Now, this next part, Pauli exclusion principle, Hund's and Aufbau's principles still apply. What does all that mean? Those were the principles that I sort of told you about and said, make sure you know the basic ideas and you can follow it, but I don't care if you match them up. These were the ones that said, can I have 2 electrons going up in an orbital? No. The one has to be spin up, one has to be spin down. They were the ones that said, how do you fill across a p orbital? Do you fill 2 in the first one and then 1 by itself, or would you go 1, 2, 3 across? 1, 2, 3 across. Those are all of those rules. You're going to treat those exactly the same. It hasn't come up yet because we've just been dealing with s orbitals. Same rules apply. So now let's actually do these so the rules make sense. Okay, so these are your second row diatomics. So not counting the first 2 that we already did. These are the ones that you have to be able to replicate if I handed you a piece of paper and said, do this, okay? As your book goes on, it'll get super complicated, and I'll tell you exactly what you do need to know. But for your reference right now, you should be able to replicate this slide like on your own with a blank sheet of paper. I'm not going to actually do that and hand you a blank sheet of paper and say, make this, but you should be able to if I wanted you to. Okay, so boron. So first step is make the atomic level diagram. So I've already drawn this in for you just for the sake of time, but I don't have to draw this in for you, right? On an exam, I can just say, make me the MO diagram of boron, make me the MO diagram of carbon. But for the sake of time, I've drawn it in for you. So if we write in the valence electrons for boron, it looks like that, right? 3 electrons. So I did this for each side. I've done this for boron here. Now, now comes the next part if you look at your slide where I say decide on the order of the diagram. Look at these, boron, carbon, and nitrogen, and now look at oxygen, fluorine, and neon. What's different about the ordering? It's pi sigma. So right here, we have sigma is higher than pi, sigma is higher than pi, sigma is higher than pi, pi is higher than sigma. Now, what are these pi's and sigmas referring to? These, right? The types of bonds. So the ways that we overlap them. So we overlap them one way and we get this. Is that a sigma or a pi? Same rules apply as with hybridization for this one. It's a sigma, right? End on end, it's a sigma. And then these are a pi. That's why we have 2 pi orbitals, right? We have 2 different versions of this. We could overlap them in one dimension or the other dimension. Okay. So back to this then. So that's how we get this pi and this sigma. Now, for each one of those, we have a bonding and an anti-bonding. So these are our bonding orbitals. These are our anti-bonding orbitals. So what I mean by decide on the order is basically for this slide, is it boron, carbon, or nitrogen? You're going to do this ordering. Is it oxygen, fluorine, or neon? You're going to do this ordering. Okay? Now, a question that may be running through your mind is, where in the world did I get this from? Right? I've just put up this whole picture. I have not really completely explained how I got this. Basically, people plugged in all these equations into computers, just like when I showed you the pictures of the orbitals, and I said, hey, this is what the probability densities look like when they're all mapped out. Same rules here. People plug this into a computer and they calculated these and they see what they look like, and then they match up really well with experiment. So that's where these come from. So that's why we know that this is a different order here than here, okay? Now, if you look at this in your book, you'll notice I made my own diagram up. This is based off of my PChem book, not your book. In your book, they have them all at the exact same energy levels. They didn't draw it as an energy level diagram. They didn't sort of designate that out for you. So it looks like it just flip-flops here, like there's some magical thing that flip-flops. If we look at mine, what do we notice about this flip-flop here? Is it really just a flip-flop, or what's happening here? It's a slow gradient, right? It's that here this happens to be quite a bit higher, and then it goes lower and lower and lower. I don't care that you know exactly these orderings here. This isn't to scale or anything of that sort. I just wanted to get across the idea that this isn't just this magical point where it flip-flops. It is a gradient, and that these are levels that someone calculated, that the computer will calculate for you. Okay? So when that middle bulletin point on the last slide, when I say decide on the ordering, for these, you have to know that for this grouping, the sigma is higher than the pi. And for this grouping, this pi is higher than the sigma. Does that happen up here with these? No, those are the same, right? So it's just these bottom two of the p that you have to worry about. Now, if you've maybe flipped ahead in your slides or glanced ahead, you notice I don't put any of the other diatomics from the periodic table on there. What do you think that means? Do you have to memorize all the diatomics for all the periodic table? No. As far as we're going to go for what you have to know the ordering for is here. Okay? We're not going to go on, and I'm not going to make you memorize any more than this. So this is the sort of thing that you need to know, and you need to know how this flip-flops. Okay, so let's actually make these diagrams now. So we have this. We've decided that the order is pi is lower than sigma, because I've drawn it out. So how many electrons do we have total to work with? 6. So we just fill them in. Notice what I did with the p. Did I put spin up, spin down here in one orbital? No, you filled them across, right? Just like you did with your p orbitals when we were drawing the atomic level diagrams, we do the exact same thing here. We spread them out, okay? What's the word for this? We have 2 orbitals that are at the same energy level. You remember? Yeah, degenerate, good. A couple of people remembered. So remember that phrasing too, right? If I were to say, what does it mean if the two orbitals, are at the same energy level, you would say that's degenerate. So make sure you know that terminology. Okay, let's move on to carbon. How many valence electrons? 4. So we fill them in. You have to fill that in order to get all your points. You can't just leave it with just the MO diagram. You have to, again, remember all of these subscripts. So notice what changes here. Our subscripts here is 2s, right? Where does that come from? Well, here. We took them from the 2s orbital. What do these come from? 2p. Good. Okay, so how many electrons? Oh, yeah.
How come, when you do lithium or the other one, you start at 1s, but then you do more on 2s?
So you can fill in the 1s for these, and I think in your book they do. Personally, I don't care if you do or don't for an exam, because they're all going to be the same. And so it gets a little redundant. All I really care is valence electrons, because that's where you're going to be filling into. Your valence electrons are the ones actually doing the bonding. So if you just do your valence ones, you're fine. And honestly, for lithium and beryllium, if you just do 2s, I'm fine with that too. You don't have to draw in the 1s if you don't want. For bonding, bond order purposes, it doesn't actually make a difference, because when you fill in the electrons, they cancel, right? How many would you have in the bonding orbital of 1s? You have 2. And how many would you have in the anti-bonding orbital? 2. So they would cancel out anyways. So it's drawn both ways. Okay, so now we have 8 electrons. So we can draw them all in. Now, for nitrogen, we have 5 valence. Hopefully you're kind of getting the pattern here, so we'll go a little quicker. So how many electrons total? 10. So we have this. Next one. We end up with 12 total. Yeah, 6 each, so 12 total. Good. So we end up with that. Are you catching the pattern, hopefully, here? Any questions as we're doing this? This slide kind of gets redundant if I talk too much on it. So, okay. So this is sort of the max that you're going to have to replicate from scratch without some information from me. Any of these are free game for me to say, draw the MO diagram of nitrogen without any other information. Now let's go through and calculate the bond order since it's a little bit more complicated. Exact same rules apply though, right? Are there any questions? It looks like maybe there's a few. Oh, there.
The top with a star on the very top, is that a 2s or 2p?
Oh, good catch. That's a 2p. That should say 2p. Thank you. And I will fix that on the slides and post it too. Okay. All right, so now to go through and calculate bond order. So how many do we have in bonding orbitals here? 4, right? 1, 2, and then these 4. How many in anti-bonding orbitals? 2. So our bond order then is 1. All right. You'll sort of catch also the pattern that these just all cancel out. And so if you're doing this sort of on the fly in your head, which some of you like to do, then that's perfectly fine. You can actually sort of ignore these and notice that they cancel out. If you're calculating it, same sort of thing, but it doesn't make a difference either way. So next one. We have how many electrons in bonding orbitals? We have 4 here, but then don't forget these. So 6. And how many here? 2. So 2 total. Okay? All right. N2. So we look at this and we say, well, how many do we have in bonding orbitals? Well, we have 6 here and then 2 here, so 8. And then how many here? So we get a triple bond. Okay, next one, oxygen. So how many in bonding orbitals? 6, 2 is 8. And then how many in anti-bonding? 2 and 4. So we end up with a bond order of 2. Go through these a little bit slower at home too. And make sure that you can do this kind of all from scratch. Okay, now fluorine. So same rules. So we have 2 in bonding orbitals here, 6 in bonding orbitals here, 2 in anti-bonding here, 4 in anti-bonding here. So we get 8 minus 6. So you're counting everything that's not in an orbital that's a bonding orbital, so it doesn't have a star next to it. We're counting those as our bonding electrons, and anything in the orbitals that have the star on it, the anti-bonding orbitals, we're putting those as a subtract. And the neon, of course, is 0 because it's completely filled. Okay? Yeah? So, well, as far as the practical significance, it'll change some of your bond orders around a little bit on the lower levels. Well, actually, it doesn't even do that. It'll change whether it's paramagnetic or diamagnetic in some cases, though. As far as how it comes about, it's because of the calculations. It's because when you actually plug these into a computer and you actually get the energy values out, the sigma happens to be a little bit lower than the pi. And you don't really have to worry too much about why that is, other than that it is. And then your second? You mean as far as, I'm not sure what you mean. Oh, okay, so her question was, is there any way to know, you mean for like calculating the bond order and such? Her question was, do you know is there any way to figure out how many electrons are bonding in the bonding orbitals or the anti-bonding orbitals without making the MO diagram? Not really. I mean, if you get really good at it and you can think about it in your head, you could do that, but you're still creating the MO diagram. And honestly, these are a little tough to do that with. You can get kind of quicker at it because if I don't ask you to draw it, you can just sort of draw out the lines without having to draw out the pi's and the sigmas and labeling them, but you really kind of have to create them to see it. Yeah? Yes. So, okay, her question was, do you use these charts for anything other than diatomic molecules? And the answer is yes. And for your own sort of entertainment and knowledge, skim through your book over the section that has, and you can see that they do it for water, and you can see that they do it for benzene. That goes a little bit beyond the scope of this class, so we're gonna leave that be. You'll talk about it a little bit in organic chemistry to describe some things like how benzene works. And then if you take physical chemistry, you'll talk about it a lot. But in this class, we're kind of gonna let it go at diatomics. Now, something that we will cover is heteronuclear diatomics. You won't have to know the ordering. Like for instance, whether pi and sigma are flip-flopped like this or like this. But I'll tell you that and you can create them. And we'll do that in a minute. You can use them for much more complicated molecules. There's this point where in this class there's a level of memorization to it that loses a little bit of value. There's another hand up. Yeah. Okay, so her question was, for the atomic orbitals diagrams on the side, do you have to draw everything in, or specifically the electrons? Yeah, you have to draw in the electrons and make sure you label them too. On exams, this one tends to be one where people forget to label them and they forget to fill in the electrons because they're so busy concentrating on this part of it, but you really need to have both. Anything else? No? Okay. So now let's do this for ions. So same sort of rules apply as all of the things we've been doing before, but now we're going to do them on the MO diagrams. So we add or subtract electrons as we need. So if something is a negative ion, are you going to add electrons or subtract them? Negative ion, add or subtract electrons? You're going to add, right? You have a negative ion, so you need an extra negative charge, so you add in an electron. What if I make it a positive ion? Take an electron away. So same rules as always apply here. Make sure you take them away properly. You're not going to take two from the same orbital if you're in the pi bonds. And same rules apply as before. You're going to start low and build high. You start with the low energy electrons or low energy orbitals and go up to the higher energy orbitals. Now, what I mean here, this doesn't apply to homonuclear diatomics. Now, homonuclear, that means same nucleus, right? So heteronuclear would mean different nucleus. So keep that in mind when you're thinking about things. So far, we've only done the homonuclear ones, and that's just because they're a little bit simpler to deal with, and so we're starting there. But when we get to where we're doing heteronuclear ones, you're always going to give the electrons to the electronegative atoms. Where are you going to take the electrons away from? The non-electronegative or the electronegative? What does electronegative mean? Think about that for a sec. How much it wants to pull electron density toward it. So if we have to add in an electron, are we going to want to give it to the thing that wants a lot of electron density or the thing that says, nah, I don't want that electron density? Yeah, the thing that wants it, right? So if you're adding in electrons, give it to the electronegative atom. If you're taking away electrons, give it to the more electronegative take away from the more electronegative or take away from the less electronegative. Less, right? It doesn't want a lot of electron density, so take it away from there. Now, does that matter when we get to the MO part of it, the middle part of it? No, we're still just counting electrons and filling them in from low to high. So let's do this real fast. So we'll start with nitrogen. So this is straight from your other atom or your other diagram that we drew. I put it here just so that it matches with the charges. So this is a homonuclear one, so it doesn't really matter where we add or subtract from. We should do it symmetrically once we get to a charge of 2. Okay, so let's do the N2 plus first. So if we have a plus ion, are we going to take away an electron or add an electron? Take away. Does it matter where we take away from over here?
Nope.
Nope. So we fill in. I took away from the one on the left. It doesn't really matter. Now we count how many electrons we have, which is 9, and we fill in. Okay? All right, next one. So let's do this one. So we have a negatively charged ion. So what are we going to do? Add or subtract an electron? Good, we're going to add an electron. Does it matter where we add it to? No. So again, I added it to the left, but it doesn't really matter. And when we fill in, now we have 11 electrons. So we get this. Okay. So -2. So we've now added in 2 electrons, or 1 more from here. Now does it really matter where we add it into? We should keep it symmetrical. So we should add 1 to each side. So I've added 1 to this side and 1 to this side. So when we go to fill in, we have this. Now notice here, same rules apply with the ions that applied with the regular atoms or molecules, that I fill in 1 here and then 1 here. I don't put 2 of them in 1, right? When you have degenerate orbitals or orbitals of the same energy level, you fill across first and then you double up if you need to. Okay, so now let's look at the bond orders for each of these. So what was the bond order for nitrogen? Well, let's recalculate this. You're right, but we'll recalculate it since we didn't seem to have a large agreement. So how many are in bonding orbitals? We have 6 here and 2 here. And how many are in antibonding orbitals? 2. So we have a bond order of 8 minus 2 divided by 3. Or I like to just kind of think of canceling these out and then taking the 6 and dividing it by 2, either way. So we get a bond order of 3 for nitrogen. Okay. Now, what do we think is going to happen when we add or subtract electrons? So let's look at the adding or the subtracting of an electron. What do we think is going to happen here? Is the bond order going to go up or down? It's going to go down. Why? Where did we take away an electron from? Yeah, we took one away from the bonding orbital, right? This one right here, that's a bonding orbital, and we took an electron away from that. So do electrons in bonding orbitals add to a bond or subtract from a bond? They add to a bond, and we took one of those away. So this one should be lower. Now let's look at this one. Where did we add an electron to? A bonding orbital or an antibonding orbital? Antibonding. So is that one going to be lower or higher? Okay, let's think about it again. If you add an electron to an antibonding orbital, does that add or subtract from the bond order? Subtracts, right? Antibonding. Think antibonding. It keeps it from bonding. It subtracts from the bond. Okay? So antibonding takes away from the bond. Bonding adds to the bond. So now we added an electron to an antibonding orbital, an orbital that keeps it from bonding. So is it going to have a lower bond order or a higher bond order? Lower. Is this one going to be even lower, or is it going to go back, or is it going to be higher? Even lower, right? Because we've added another one. And if we made it another minus, if we made -3, it would be even lower. So now let's calculate them all out and prove this. So if we take this and we calculate all of our electrons that are in our bonding orbitals, so that's 2, 4, 6, 8, and all of them in our antibonding orbitals, we get 2. Okay. Now if we do it for this one, we get 2.5. And we know what nitrogen is already. We've done that one. It's 3. And we do N2 plus. So now we have 2, 4, 6, 7 minus 2. We get 2.5. Does that make sense with what we just talked about? Well, we started with a bond order of 3, and we took away one that was in a bonding orbital. Would we expect it to go down by 1/2? Yeah, right? Because electrons add or subtract how much of a bond? 1/2. And if you forget about that, you can think about the fact that we have always talked about a single bond having 2 electrons, right? So each one's 1/2. Now over here we added one, and we added it to an antibonding orbital. So that went ahead and subtracted 1/2 as well. Here we subtracted a whole one, but that's because we've added in 2 electrons and both went to an antibonding orbital. Okay? So this is how you do ions. We'll eventually get to one where you have to worry about electronegatives and stuff, but this one we don't need to. Okay, so now I want to take a minute and look at a case that I think is fairly interesting, and that's molecular oxygen. So this is the MO diagram for molecular oxygen. I took it straight from the other slide where we started with oxygen. Now there's some things to notice about this. First of all, what's the bond order? It's It's 2, right? And I got that because how many are in bonding orbitals? 2, 4, 6, 8. How many are in anti-bonding orbitals? 2, 4. So we get a bond order of 2. Now, is it paramagnetic or is it diamagnetic? Maybe we should have a refresher on what paramagnetic and diamagnetic means. Okay, paramagnetic. Does that mean unpaired or paired electrons? Unpaired. Diamagnetic, paired or unpaired? Paired. Paired. Okay, so now we have paramagnetic equals unpaired, diamagnetic equals paired. Is this paramagnetic or diamagnetic? Paramagnetic. Good. Okay. We can agree upon this, right? Now draw the Lewis structure for oxygen. No, really, draw it. Just take a few seconds and draw the Lewis structure. Forget about MO diagrams for a second and just draw the Lewis structure for me. Not everyone is writing. Okay, what does it look like? Is that what you got? Okay, so does that have a bond order of 2? In this way of thinking about it, is it a double bond or a single bond? Well, it's a double bond, so that's a bond order of 2. Is it paramagnetic? No. Okay, well let's draw it paramagnetic. I can make it paramagnetic, right? I'll take one of these bonds and I'll just draw it like that. Okay, now I have it paramagnetic. But what did I screw up when I did that? The bond order. Now I have a bond order of effectively 1 there. Okay, well, how do I draw this then to make it so that it has a bond order of 2 and that it's paramagnetic? You don't. You can't really do it. So it's one of those situations, so then what does experiment say, right? That's always what we should go to. We should say, well, which one's right? Is MO theory in this case right, or is it going to be this Lewis structure model? Well, let's go to the experiment. If I were to take and I were to, pour some liquid oxygen over a magnet, you would see that it really is paramagnetic. So that's true. It is definitely paramagnetic. And the thing is that when you measure the bond length, we have ways of doing that. The bond length comes out to be 2. So we can't actually accurately represent it like this. It doesn't actually, one or the other is sort of not represented properly. But with MO diagram, we can actually represent exactly what MO theory, or exactly what experiment says. So when I originally had said that, hey, MO theory is a little bit more complicated, but it's a little bit better at explaining things, it's cases like this that come up. There's not a ton of them, but it does come up. Okay. All right, so next one. Let's do carbon monoxide. So this is the first time I've shown you a heteronuclear diatomic. Now, rules for these, for what I can test you on, I can tell you to draw me the MO diagram of something like CO or NO or something of that sort, but I have to give you some hints. I have to tell you the order, okay? So you'll notice Sapling will do this too. They'll tell you to draw a diatomic, and then they'll tell you the ordering of the energy levels. This is what they're getting at. So in this case, I've just drawn this out for you. On an exam, I wouldn't have to draw it, but I would have to say, well, we have sigma 2s star, pi 2p, pi 2p star, and then sigma 2p. There is a copy-paste glitch, so make sure you change all of these to p's, and I'll fix that, but it's a glitch. It's a systematic copy-paste glitch. Okay, so let's look at this. First of all, we're going to do some other things other than CO. So why don't noble gases form diatomic molecules? And use a MO diagram to prove it to me. So this one doesn't actually have to do with CO. Look at your helium. Look at your neon. What is your bond order on all of those? 0, right? So what happens is that if you were to form a bond, you would have the exact same number of electrons in the bonding orbitals as the anti-bonding orbitals. And so it's going to be pulled apart. You're going to have a bond order of 0. There's nothing that's going to be holding it together. So an MO diagram, if you draw it out, would show a bond order of 0. Okay, we have 2 more examples to do. I'll do it next time. Notice your Sapling homework deadline did get moved back. We didn't make it quite as far as I hoped. Not a big deal. So your Sapling deadline got moved back a little bit.